we're now going to look at the topic of fitting univariate functions. And that means basically n equals 1. So the so-called feature vectors or independent variables, x is just a scalar. Now what that means is we can actually do a scatter plot of the data. So for example, I could just, this is x, this is y, and my data might look like just a bunch of points like that. Okay, so I can plot them like that. And that's a scatter plot. Now, when I create a model function, y hat equals f hat, it's a function, and I can evaluate that for every value of x, so I can plot a curve, right? I mean, so it might look like this there. And that would be my, this would be f hat. And so we'll be able in this case where the dimension of x is 1, so n equals 1, your eyeball can actually judge how well we do. Of course, we'll also check things like the RMS error and things like that. But your eyeball should be able to take a look at it and say, we're doing a pretty good fit here. Okay. So beyond the constant fit, which we saw last time, we're going to look at what is, maybe the simplest fit after that. It's going to have two coefficients. So p is 2, and the first basis function is 1. Once again, it's the constant function 1. And the second one is just x, like that. And so what that says is that your model has this form. It's f hat of x equals theta 1 plus theta 2 x. So that is, that's the model. And of course, what we have to guess is, or choose, are theta 1 and theta 2. Now, in this case, it's like the previous one with the constant model. It's very, we can actually write out what A is. A is this. Now, let's remember what these are. The rows here represent different data points in my data set. Then the first column tells you to evaluate your first basis function at those points. But you know what? That's always 1. So that's why you see all the 1s here. Okay? And in the second one, I simply just take x and I just replace it here. So that's x1, x2, x3, and so on. Now, that's an n by 2 matrix. I can form A transpose A and invert it. And I don't need to use some fancy numerical thing. I mean, I'll say a little bit about it in a minute. It wouldn't hurt me if I did. But the point is there that a 2 by 2 matrix is, that's something we can actually work out the inverse of. You know it. That's one of those things you're just supposed to memorize, like the quadratic formula. And so you can actually work out what theta hat is. And it turns out that you can write the predictor in a very specific way that's actually highly interpretable. Yeah, and I should add, you don't have to do this. This is just for interpretation. The truth is there would be absolutely nothing wrong with the following code if you were going to do this. Is first, build that matrix. Step 1. Step 2, you write theta hat equals this matrix. Now I'm writing code. Now, first I'll write it in non-code, A's pseudo-inverse times, and here, y, yd, I think is what we call it, right? That's the data, the vector of data outcomes. Okay, now in code, you would maybe, depending on the system you're using, it would look like that. It would be some kind of backslash, right? Right. In other ones, there would be some least squares method you would find or something like that, and you would call that special function. Okay, so there's absolutely nothing wrong with doing this. So working it out and having a so-called analytical formula for it is just for interpretation. It offers absolutely zero advantage in any other way, right? It's just for interpretation. Computationally, certainly this is just as good as anything else. Okay, now it turns out it looks like this is super interpretable, which is cool. It says we are going to predict the following. Well, let's take a look at it. So first over here, it's going to say take x and divide by the average, subtract the average of x from it. Oh, and by the way, look at this. You actually are going to divide by the standard deviation. And if you see the part that I have boxed here, it is the independent variable x minus its average divided by its standard. That's super interesting. That's its z-score, right? So this is a number. And it kind of typically is between -1 and +1. That's what it is. And it's highly interpretable, right? So if it's plus 0.5, it means that you are about 0.5 standard deviations above the mean. That's what it means. Okay. And then it says you're going to multiply that by the standard deviation of y. Rho is the correlation coefficient between x and y. And then to this thing, this is the part that depends on x. And then to that, you add a constant, the average of y. And so it's super interesting. If x and y are uncorrelated, then rho is 0. And this whole second term, this just goes away. And it says here's your best straight line fit, the constant model. In other words, you just take theta 2 equal to 0. Okay? And that makes perfect sense. If two things are uncorrelated, it says that when one is high, you have no right to make any claim about what the other one is doing. And that's exactly what it says. You might as well just guess a constant. If the correlation is high, like rho is near 1, it basically says that whenever this is positive, so should be your prediction should be above your average value. So this is the idea. It's actually it's just a nice formula to interpret, but as I said, computationally, it offers no advantage of any kind. Okay, that gives it. Oh, and this is called the straight line fit because the graph of that is a line. That's an affine function, of course, right? So, and some people would say this is a linear fit or something like that. And as we know, that's not a linear function and so on. So that's wrong, but whatever, just give them a break, I suppose. You could say something, actually. You could say, in the right social circumstances, you would say something like, hey, just for the record, that function is not linear, it's affine, but it's cool if you want to call it linear, keep going, but I know what you're saying. Okay, so, and that's, I think, why this is called the straight line fit, because the graph is a line or it's an affine function. Okay, so here's an example. This is one that should basically kind of be burned into your mind whenever someone says least squares data fitting. This is the picture you want to see. And so here's x, which is a scalar, remember, so we're only looking at one feature, and here's y. Now, and they're a little bit faint, but you can see the little green dots. Those are our data points. I don't know how many I have. Doesn't matter, 50 or something. And the blue line is the so-called straight line fit, right? And now what's being minimized is each of these points has a height or a depth above or below this plot, right? So these are what I'm drawing with my pen right now. These are the residuals, right? Because that's the data point. And then from that, you subtract the value of the model for that point. But the value for the model is the height of the line, because that's what I'm drawing, is f hat. So what this line does is it minimizes the sum of the squares of the little vertical lines that I've drawn. And the length of the little vertical lines is the magnitude of the residual. So that makes perfect sense. And even, actually, just this is quite useful in a bunch of applications. So here's one. It's actually a very important part of like all of finance. And it goes like this. In that context, x here, which is a scalar, is the return of the whole market, let's say daily. Okay, so it's plus 0.01 means it went up 1%. It's minus 0.02 went down 2%. That's what it is. And then y is the return of a particular asset, right? Like, so for example, for every day I would get how it doesn't really matter, the Russell 2000 or whatever it is. Did that go up or down 1% or whatever it is? And then I could find out, well, how did Apple do or Google? And that would be y, right? And I would get a whole bunch. Well, every day I'd get a pair, x and y. So those would be the return of the market and the return of, let's just say, Apple. Okay? So now what we're going to do now is make a straight line fit that essentially predicts the return of Apple from the return of the market. And that's usually written it's an affine function, of course, but it's usually written in a specific way. And I'll show you what that is. It's y hat, that's our prediction of the return of Apple, is equal to the following. It's equal it's an affine function, and it's written several ways. So one is this. It's written as a risk-free rate plus alpha. Now, risk-free is something like U.S. Treasuries. It's supposed to be a risk-free it's the risk-free interest rate, right? So it would be the daily one. That's extremely well approximated by 0 right now, but okay. So that's the risk-free interest rate plus alpha, and that's instead of using theta 1, they use the parameters alpha and beta plus alpha, and then plus beta times now x minus mu market. Mu market is the mean market return. Okay. By the way, for daily stuff, that's just about 0. It is true that the market goes up, 15% per year. But if you divide that by 250, you'll find out that that's a pretty small. That the amount it goes up each day, the mean is relatively small. But anyway, That's the mu market. And so if that is positive, it means that the market went up more than its average that day. If it's negative, it means it went down or not as much as its average. Then beta is what multiplies that to form the prediction, right? So, okay. So these are referred to as literally, like in this case, it's Apple. You would say this is Apple's alpha and Apple's beta. And by the way, I should say that there's not, people use some slightly different formulas. They divide by, I don't know, they normalize things. So there's slightly different definitions of these, but always the rough idea is the same. I should also say that some hardcore economists would argue that alpha is zero, that there can't be any return, that alpha has to be zero, and they would argue that if that wasn't the case, there'd be arbitrage and blah, 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 and long, complicated arguments. I can guarantee you that many people working in hedge funds will tell you that is false empirically. Their alpha is not zero. Okay, so this is so widely known that people just refer to the maybe not the alpha, because some people even dispute its existence, but certainly the beta everyone agrees on, and you just say, hey, what's the beta of Apple with the market? I don't know what it is, right? But the betas range from about 0.3 to 1.5. I don't know, something like that, right? But this is a rough idea, and it's actually so people just say that they would say, oh yeah, well that's that's the beta with the market or something like that. So okay, and this is nothing but a straight line fit. The only thing you're doing is you're making an affine model or straight line fit to predict the return of a particular asset. You're predicting it from the return of the whole market, right? So that's the idea, right? So if beta is 1, basically says if the market's up 1%, you would expect your asset to go up about 1% too. Okay. Another use of this is in time series. So here, actually what we do is xi is like a timestamp. And for simplicity, we're just going to take xi equals I. And that means that basically you have sampled a value, y, at equal times. They don't really have to be equal, right? For example, in trading and stuff like that, it would be on trading days. And trade, so it would go like, Monday, Tuesday, Friday, and then it jumps to Monday again. So it's not actual equal time. In some cases, it is equal time, right? If it's something like you're looking at the temperature or rainfall or humidity or something like that, where there's no weekend, well, there's a weekend, but it's not relevant, then you would, these would be evenly sampled. Okay, and so when you form a model, a straight line model for a case where x represents time, and in fact, in this case, we're just going to make it I, right, which literally means the number of periods. That's called the trend line. It's very cool. And if you subtract the trend line, that is called the detrended time series, right? So all this makes perfect sense, right? So and theta 2, you would say, is the trend coefficient, and it tells you that this increases. I mean, if theta 2 is positive, it tells you the approximate increase in y when you go from yi to yi plus 1. Which is kind of cool, right? So that and all highly interpretable. Okay, so let's look at an example. So on the left, what you see is if you look at the data, those little green circles, they're hard to see here, but you can look at the book or something like that, or they're not that hard to see. That's the data, and the blue line is the trend line. It's nothing but an affine model. It's absolutely nothing more. And you can see kind of cool stuff. You can see that, for example, there's some weird oscillations in here, but it kind of more or less looks like the trend line. In fact, you can see some interesting things. This is petroleum. This is world petroleum consumption, and you can see things like, look, it's a little bit below the trend line in 2008 because there was a huge financial crisis, right? Just as an example. And I'm not sure what some of the others, but I'm sure someone who knows about this stuff could tell you stories about why it's above or below. That's the trend line. Now, what you can do then is you subtract. Oh, by the way, so all sorts of interesting things. The slope of that trend line, in this case, has a beautiful interpretation. It is literally, it's our prediction of the number the increase in the number of millions of barrels per day that are used when you move forward one per year. That's how much consumption is increasing. Okay, now if I subtract the blue line from the green data, I get this, and we've done that, but we've also drawn lines in between things to just to make it easier on the eye, just so you can see it. And you get something really cool that looks like this. Now, it's very cool. It shows you in which year how close were you to the trend line, right? So in like these years, you were pretty close, right? It was like pretty close to the trend line. Here you were below. Here you're above. I don't know why, but there's probably some reason for that. So that's it. And here you could see other stuff, like there's some weird cyclical stuff, and I don't know, somebody might mumble something about a business cycle or something. I don't know. I'm just making that up. So this is very, very common, is you would see so-called, so when someone tells you, oh, here's the data, and here it is detrended, it means that they fit a straight line model, and they subtracted the straight line model. And so what you get are the fluctuations around the straight line model. So, and this can reveal interesting stuff. And it's a whole lot easier to understand, I think, this plot than, well, no, this one is a good one to see first, because it says basically to first order, it's increasing linearly. It's a pretty good fit. And what this shows is the kind of the deviations from that, and tells you, it reveals other structure, like when is it above, when is it below, and so on. Okay. Well, if you can do a straight line fit, the next obvious thing is to move to polynomials or something like that. But we'll see. There's lots of you have lots of flexibility in how you choose your basis functions. So here we're going to take fi of x is x to the I minus 1 for I equals 1 to p. So that means that f1 of x is equal to x to the 0, which is 1. That's our friend, the offset in the model. f2 of x is going to equal x to the 1, which is just x. F3 of x is going to be x squared, okay? And so on. Now, when I form a linear combination of these functions with coefficients given by theta I, those are my model or parameters or coefficients, I get a polynomial of x, right? So here, f hat is exactly this. It's theta 1 plus theta 2x plus up to theta p x to the p minus 1, right? Because I'm taking p to be the dimension of the number of basis functions I have, okay? So it's just a polynomial. And in this case, that matrix A, which remember what it is, the rows tell you about the different data points, and the columns tell you about the different features, right? So, for example, the first column tells you about this first feature, this first basis function. The first basis function is just 1, and that's why you see all these 1s. The next one is just x1, x2, and so on. That's because of this guy here. And the next one would be the squares of them, and so on. So this matrix comes up a bunch of times. It's called a van der Waals matrix. I think we've seen it before. You don't have to know the name. Doesn't matter. It just happens to have a name. It's named after a mathematician, van der Waals. And we've seen it before in, for example, polynomial interpolation. So it's not surprising. Okay. And so the idea is if I put theta here and I multiply it by a times theta, what I'm going to get is actually a polynomial evaluated at the points x1 down to xn. Okay, so and then we just use as usual, it's going to look like this. If you're going to write code for this, it would start like this. The first thing you do is you write a little code snippet that forms the matrix A. Okay, so you'd form this matrix, and you could, depending on your language, you could do it all sorts of clever ways. And the truth is, in some languages, you'd have some function called van der Waals, and it would literally form a van der Waals matrix for you. With the values, you'd have to give it the values x1 down to xn, and then it would simply form a van der Waals matrix. But again, not relevant. You form the matrix. That's a little snippet of code. And then you simply do this. And now I'm writing code. I'm not writing math right now. I'd write theta hat equals a backslash, and then it's going to be yd, which is our vector of outcomes, right? So that's what my code is going to look like. In fact, that's what your code is going to look like when you do this, and you will be doing this. There'll be literally, that's the template. The template is there's a section on top that says form the matrix A, which literally says evaluate fi at xj. and so on. I said that the other way wrong. It's actually evaluate at fj at xi. Sorry. Okay. And then it's kind of a letdown at the end. That's the actual line that does the actual fitting. And then you might do things like plot the results or try to figure out or look at the RMS error or things like that. Okay, so let's look at an example. So here we have 200 points. They are the green dots here. And you can see it's not like they're completely random all over the place. You know, they're kind of high here, a bit low here, and so on. And so here is the best quadratic fit. That corresponds to p equals 3. I have 3 coefficients. I have theta 1, which is the constant. Theta 2 is the linear term. And theta 3 is the quadratic term. And so here you can see this thing kind of curves down. So theta 3 is negative in this case, right? That's our interpretation of this. Now, here's a fit of degree 6, and that means I have p equals 7. I have 7 coefficients. And if you look closely at it, you'll see that it's actually capturing some real nuance in the data. For example, it's kind of going up rapidly, has a little weird bend there, goes down rapidly, kind of comes up here. And so, you know, it's doing pretty well. And here it is, degree 10. I mean, here we're really hugging the data pretty closely in some cases. And here it is at degree 15. And it's now it's catching all sorts of weird stuff in the data. Okay, so so this is just a picture to show you what it looks like. You can do this. This is like 5-10 lines of code. You could do this yourself, and you'll get results like this. By the way, what this brings up immediately is the question is, what degree model should I use? Okay, and we're going to answer that in maybe the next section or soon. We're going to answer that question. The answer to that question is not totally obvious, right? Because if you simply wanted to do the best you could on fitting your data that you've got, you should use as big a degree as you can handle. We'll see what the problem with that is soon, but that's later. The final topic in this section is the idea of, we've already seen regression, and then this is so-called linear in the parameters data fitting by least squares. And they're very closely related. In fact, the truth is they're really kind of the same thing with 2 different notation conventions. I'm using mostly the conventional notation, although I think my statistician friends still cringe when they see some of the things I write down. They don't like me writing the matrix A, for example, for the coefficient matrix, but whatever. It's pretty close. But what I want to do now is just elucidate what the difference is between a regression model and one of these linear in the parameters model. The fact is they're just not that different. So here's the way it works. Recall the regression model looks like that. It is basically it's an affine function of the feature, period. So here, highly interpretable, for example, beta 3 tells you how much x3, the third feature, figures in your prediction. V, the so-called offset, that's a number which is our prediction when the features are all 0, when x is equal to 0. Okay, so this is the regression model. Now we can make a regression model fit our general framework. All we use is the following basis functions. We use f1 is 1. We've seen that many times so far. And then fi of x is xi minus 1. So literally, the f's are, the first one is 1. The next one is x1. That's actually what we would call f2 of x is x1, and so on. And so in that case, you get exactly this. Our model would be a linear combination of these basis functions. That's theta 1 plus theta 2x plus theta all the way up to n plus 1 xn. And then we would simply write that as x transpose theta. Remember that that's a slice. That means that the second through the nth component, they're the ones that multiply x you see directly here. And then theta 1 is our offset. That's the same as v. So what we can see is that we can represent regression in our general data fitting framework here. Okay, so regression is a special case of linear in the parameters least squares fitting. Now it turns out the opposite is true in a weird way. That suppose we have a general fitting model That's f hat is theta 1 f1 of x plus up to theta p xp. And it's extremely common to have the first component equal to 1. That's called an offset in the model or a constant. In fact, it's so common that maybe sometimes a lot of systems that do this stuff for you just assume it. They don't even say it. They just say there's an offset. And you actually have to call the methods basically with a minus minus no offset to actually not have the first component be 1. But okay. Now, we can think of this thing as a regression model, but not using x. Actually using this other vector here, which is f2 of x up to fp of x. And we think of those as transformed features. So the point is that our general model it can be thought of as just regression. But what we do is we think of the f's as transformed features or feature mappings or something like that. And that's another way to think of how we do this kind of general fitting is we think of, in that case, you'd call the x's the raw features, right? And then the f's they transform them. Like, for example, if you're fitting a polynomial, they would take the 4th power or the 6th power or something like that. So that's called data transforming or feature transforming. And then you simply do regression. So they're basically the same thing. They just have slightly different notation systems. And I should say that both notation systems are kind of widely used. Next topic is a so-called auto-regressive time series model. Now this is just your first glimpse at this, but it's very powerful stuff. It's very cool. So I have a time series z1, z2. I'm going to make these. These are going to be scalars for now. Okay, so I just have a time series. Doesn't matter what it is. It could be we've seen a couple of time series, right? We saw world petroleum consumption, right? And there the index represents year. Okay, it could be hourly temperature somewhere. It could be all sorts of. It could be the price of something, or it could be anything at all. That's all. It could be some kind of economic thing, like it could literally be the GDP of a country or a region. Okay, it's a time series. There are a lot of time series, of course. And so what we're going to talk about now is something called an auto-regressive model. Auto-regressive means that you're going to let me say what the model is. The model is this. It says, we're going to use the notation z hat sub t plus 1. Z hat t plus 1 is to be interpreted as the prediction. If t is now, t plus 1 is next step. So this is actually, people would say this is the one step ahead prediction, or it's the prediction of the next value. By the way, that can be enormously useful in practice. I mean, it doesn't take a lot of imagination to imagine how useful this would be if, for example, you could predict what the temperature is going to be in the next hour or something like that, right? Or what electricity demand is going to be in the next hour, or what the price of something is going to be, in the next 1 minute or 1 second, right? So if you can make a prediction like that, that has a lot of value, practical value. Okay, so how do you make this one step ahead prediction? Well, we're going to use, you choose it. You can call it regression, or you can choose it a linear parameters model. But it's going to be this. It's going to be theta 1 times zt plus theta 2 times zt minus 1, all the way up to theta m, capital M. M is a mnemonic for memory in the model, right? So, for example, people would refer to this. I'll show you what an AR2. Sometimes people put an argument in there to say what the memory is. That's where you give capital M. And that looks like this. It says z hat t plus 1 is equal to theta 1 zt plus theta 2 times z t minus 1. There it is. And the model coefficients are theta 1 and theta 2. And it's actually beautifully interpretable. You simply say, I am predicting what the next value is going to be. And someone says, what's your prediction? And you go, well, it's simple. It's theta 1 times the current value plus theta 2 times the previous value. So if this is daily, it's like I will predict tomorrow's value to be a number theta 1 times today's value plus a number theta 2 times yesterday's value, right? And you can understand why this would be called the memory, because basically it says that your prediction has to remember the last, approximately m values of the time series. Okay, so that's called an auto-regressive model. I think it's called auto-regressive because it's a regression model, but we'll see that both the regressors and the features x and y come from the same thing. They're z's, so that's why the auto is in there. Okay, now we'll choose actually not beta here. That is a typo. We're going to choose theta to minimize the sum of squares of the prediction errors, and that's just going to be these. So let me point out what this is. Z hat m plus 1 minus zm. That's basically, this is our prediction of what the m plus 1 value of that time series would be based on only z1, z2 up to zm, period, okay? This is what it actually was, okay? And so this is like an error here. That's your one step ahead prediction error. And this is the sum of the one step ahead prediction errors across your data set. Okay, so it turns out this just goes straight in the same form. It's the same linear in the parameters model. We use y, which is the outcome, is literally it is the next value is what it is. Well, with the right indexing, and then xi we take to be these little snippets of the past m or m minus 1 values or something like that, right? So that's how this works. And so this would allow you to build up that matrix A, then you do least squares, and you get your coefficients theta. We'll look at an example. It's going to be the data is this. It's the hourly temperature at LAX, the airport in LA, in May 2016, and we've got 744 hours worth of data. Okay, on that data set, the average is 61.76 degrees Fahrenheit, and I apologize to people who come from countries that are civilized and use actual units, but sorry. Think of it as adding kind of a nice cultural flavor to it, okay? And the standard deviation is 3 degrees Fahrenheit, right? And so actually this is very nice. This says that in May 2016, if someone walked up to you on the street and said, what's the temperature going to be tomorrow? You could just say, I don't know, 61.76 degrees. And the point is the RMS error of that guess is only going to be about 3 degrees, right? That's why. It's kind of nice to live in LA. I mean, that's a little bit cold, okay, but it basically says it doesn't change. It doesn't change that much, right? Okay. Now we can compare a lot of other predictors, right? Here's actually an extremely sensible predictor. It's someone says, what is the temperature at LAX in the next hour? And here's a completely reasonable thing. You say, what is the temperature now? And they say 71 degrees, and you go, it'll be 71 next hour. That gives you an error of 1.16 degrees, right? It's not bad, right? So if you guess it, your RMS error is 1.16. It's actually not bad. It means that you're usually within about a degree. You might occasionally be off by 2 degrees, 3 even, but probably a lot of times you're within 1 or less, right? So you wouldn't be surprised if you were only off by half a degree. Okay. Here's another extremely interesting one. Z hat t plus 1. You say, what is the temperature going to be in the next hour? Here's one. You say, well, I don't know. Let's 2 p.m. What was the temperature yesterday? And you say, that's going to be my guess. Because the temperature is, roughly diurnal, meaning it kind of goes up and down, and at 2 p.m., it's, kind of about the same. It's cold at night, warm, late afternoon, so on. Okay, so this one, z hat t plus 1 equals z sub t minus 23. That gives an RMS error of about 2 degrees, almost 2 degrees. So it's better than just guessing the mean, just a constant, right? Now, if you use an AR model with 8, a memory of 8, you get an RMS error of about 1 degree, under 1 degree, right? So you're actually predicting pretty well. I mean, I guess, right? Of course, real temperature prediction models are way more sophisticated than just this. But nevertheless, this is a first cut. It's very simple. You could write the code for it. It's about 15 lines, absolutely at most, right? And it's pretty cool. And it's not clear how you would do that. And it beats these two other simple ad hoc ones. In other words, saying the temperature next hour will be simply what it is now, or what it was 24 hours ago. Well, reference to 1 hour from now. right? So those are two reasonable models. By the way, these kinds of simple models, these are very good things to do. As a practical matter, you should never jump into something fancy like an AR model. Never without doing the simple, obvious stuff first, because, well, for many reasons, right? One is if the people you're working with or for have any sense at all, which is hardly a given, but if they do, they and someone rushes in their office and go, "Oh man, this is crazy! I can predict this within plus minus, within 15 cents. It's crazy." That they should immediately ask, and it's you could flip the roles. So this is you, somebody running into you, all excited, and you'd say, "Cool, that's great. I'm glad you can predict it within 15 cents." And you say, "Can I ask what's the standard deviation?" And if the answer is like it's 14 cents, then I don't know, get rid of the person, something like that, right? No, but the point is that you would always do the simple stuff first, just if for no other reason to see how much the fancy stuff is buying you, right? And of course, you have to be emotionally, prepared for the fact that the fancy stuff doesn't buy you much at all. In which case, you quietly go back and someone says, and you say, "Here's my model," and you go, "That's predicting a constant." But we pay you a lot. We don't pay you to come up with a constant model. I could have said the temperature is 61.76 degrees. And at least then you can say, well, I tried. I looked at it, I analyzed it, I made some fancy models. Some of the fancy models were a little bit better, but not enough better to justify it. So that's why we're going constant. And hopefully they would understand that. Okay, so let's look at an example. So here is what we do is we take this AR8 model and we fit it. And now I'm just going to show you for the first 5 days. So that's 120 hours. I'm going to show you both the observed value and the prediction. So the green ones are the actual observed values. And I think what we can conclude is that they're actually integers, like when they said the temperature is like 55 or 61. So okay. And the blue one is the prediction of that temperature based on the previous 8 hourly temperatures, right? And I tell you, you look at it, your eyeball says that's like pretty good. That is not bad. So this is what this looks like. This is actually, these are some of the models that come up very quickly and can be very impressive in the right settings, right? Where you just fit an AR model to a time series. And boy, you can impress your friends and your coworkers and things like that.